Hello, and welcome to SETI Live. I'm your host, Beth Johnson, Communications Specialist here at the SETI Institute. Welcome in to our viewers from around the world. Thank you so much for joining us. Please let us know where you are watching from. Also, welcome to listeners on the podcast version of SETI Live, available on most podcast platforms. Last week, the Rubin Observatory released its first look images, including stunning views of the Trifid and Lagoon nebula seen behind us here. And an astounding cosmic treasure chest of stars and galaxies and a literal swarm of newly discovered asteroids. It was amazing. Today, I am joined by the CEO of the LSST Discovery Alliance, Beth Willman, to talk about these first look images, the future of the LSST mission, and what all this new data could mean for astrobiology and planetary defense. So welcome in, Beth. Thank you for joining me today.
Oh, thank you so much, Beth. I'm so excited to have this conversation with you.
I've been looking forward to it. I'm so glad we made it happen. So let's kick this off. So what struck you most in that first imagery? The cosmic treasure chest, the nebulae, the asteroid swarm. What got your attention and made you kind of gasp in wonder or shock or awe?
Okay. So my science background is in like galaxies and cosmology. And so I surprised myself when it was the asteroid imagery that really took my breath away. Joko, the director, was presenting the still image, right, that showed the rainbow streaks that gave the locations of newly discovered asteroids in the field of view. And I'm thinking, oh, that's great. They found these asteroids. That's exciting. And then, right, the screen pulls away. And Beth, you and I briefly talked about this before this session. And those moving squares showing the asteroids populating the entire screen just blew my socks off.
Oh my gosh, my jaw dropped. I mean, I literally was just sitting there with my mouth agape, just kind of staring at my screen going, this can't be real. How is this even real? It's amazing. In fact, I will be very nice to everybody. It's only a minute, but here you go.
Whoa.
If you want to, this is incredible.
Yeah.
Oh, this one's in Spanish. Yay! But each of these little moving dots is an asteroid. And then this split right here. Oh, 989. Look, just those numbers. Oh. So tell us how many asteroids were discovered and I want to talk about that so much. Okay, how many asteroids were discovered and how much time was spent looking in the sky? I'm going to back up because I am so overwhelmed by those asteroids. Okay, let's start at the beginning. How did this massive camera and this massive mirror perform during what was essentially an engineering first light to make sure everything worked? This isn't the start of the LSST. This is literally, can we get stuff to happen? Obviously, the answer there is yes. So, but how did everything perform? How did it go?
So the shortest answer to how did everything perform is exceeds expectations. Nice. And so, Beth, if I can even broaden your question a bit, you referred to the Guinness Book of World Records 3.2 billion pixel camera. You referred to the mirror, which is 8.4 meter diameter in glass. It's a 6.7 meter effective aperture. It's much more than that in the system whose performance was tested. It's the telescope itself, the Simone Survey telescope, which was built for speed. Beth, I need to show you a video. It's incredible how this enormous telescope moves seconds, one side of the sky to the other. And then the final component is the data management system. And the data management system, the effectiveness of that was on full display with that detection of 4,000 asteroids in 10 hours, including 2,100 new asteroids, 7 of which are not hazardous near-Earth asteroids, showing that the real-time data pipeline and the detection, which will eventually be daily updates and new discoveries of solar system objects, is already operating incredibly well, especially for this point of engineering.
It really is just a wonder of engineering. So this image behind me, you can't see it so much because we're in front of it, but can you walk us through how this amazing, enormous image was stitched together from all of the data collected?
Yeah, so there's the beautiful image behind you is one of the beautiful fields of view highlighted. And the other one was of the Virgo Nebula. That was the 1100 exposure images, 1100 images stitched together. So first is that every single picture is 10 square degrees. So it's a very large area of sky. So if you want to imagine 10 square degrees, you can hold your arm out at length. You can look at the size of your thumbnail. You can imagine 40 of those put together. That's 10 square degrees. That's one picture. And with all of these pictures that were taken, and part of the goal was to reach the effective level of sensitivity in the images as the ultimate 10-year survey. And so the multiple images in single filters needed to be added to get the depth and sensitivity. And then the images were taken in multiple colors, as you can see with your eye here in the image behind us. And there's an incredible data management team in place for the Rubin Observatory. And so a combination of science professionals who understand very well how to extract the science from the data and what the different filters and measurements need, and software engineering professionals have collaborated for a long time to write sophisticated algorithms that can put together and stack these images into full color, beautiful, photos that both have beauty and capture some of the scientific meaning of what we're looking at.
I'm stunned. I'm going to be gobsmacked for a while. So 10 hours, that's all this first look was, right? So when we talk about the LSST, which is the survey that you're all going to do, that is a 10-year plan. Mm-hmm. But what we're looking at is 10 minutes of data. And in that 10 minutes, we have these amazing images of Virgo, of the Trifid and Lagoon nebulae, of 2100 brand new asteroids. Yeah. I mean, it is kind of wild how much you got in such a short time. And as you keep mentioning, the data pipeline process for this is incredibly sophisticated as well. Can you kind of walk us through how that pipeline works? What's the process as the data comes in, and how is it getting processed out so amazingly well, so quickly?
So to answer that for a moment, I'll go all the way back to the beginning. So this has been about a 25-year project. Mm-hmm. And when this concept for what originally was referred to as the dark matter telescope, right, which is now evolved into the Rubin Observatory's Legacy Survey of Space and Time, funded by the Department of Energy and National Science Foundation. At the very beginning, it was clear that the volume and the speed of the data that would result from this experiment would be enormous. And it would really require, from the earliest days, to have a very substantial and sophisticated data management system built in. So a substantial part of the construction project was to bring together this data management team. And so what happens when the shutter closes, 3.2 billion pixels are read off that camera in 2 seconds, which itself is extraordinary. Wow. Those data go down the mountain. So the Cerro Pachon mountaintop in Chile, outside of La Serena, they go down the mountain, they go over to Chile, they go up through Florida and get distributed out to the data management centers in the world. SLAC in California is the primary DOE-run data management center. So then what happens to the data happens on 2 different cadences. There's the real-time data analysis and data processing. And that's most relevant, for example, for the asteroid detection and tracking and for the reporting. Within just minutes of those data leaving the mountain, those images have been analyzed and the measurements of the positions, the brightnesses, the suggestions of movement of objects in the image have been characterized already. And those data products are world public. Solar system relevant things get sent to the Minor Planet Center. There's also annual data releases where there's a more extensive processing, cataloging, and quantification of many different aspects of the objects all across the images obtained over the past year.
So it's an immense amount of data, as you mentioned. I know just, in some of the surveys that we're doing, what we're collecting is an immense amount of data between our laser SETI program and our cosmic program. These are all, that has kind of become the backbone of astrophysics and astronomy these days, is this massive data management that we now have to do because we're collecting so much so quickly.
Yes.
So what are the goals of the LSST? Tell us about it, because this is as we keep saying, it's a 10-year mission. This is a lot of observing time.
Yeah.
What are the goals of doing all of this observing for 10 years?
So at the heart of LSST's mission are 4 scientific pillars, and these are dark energy and dark matter, solar system, mapping the galaxy that we live in, the Milky Way, and then the transient and variable universe, the explosive and changing universe. And these 4 pillars really extend across all of the key existential questions that astronomy has to offer humankind, right? How did we get here? What are we doing here? Are there other solar systems like ours? And these 4 pillars were chosen not only for those, scientific reasons, but also because the scientific and technical requirements of each of those 4 types of science drivers stretch the combined data management, camera, and telescope system in really different ways. And so if you construct a system that can address all 4 of those types of questions, you have the most powerful system that you can possibly construct at optical wavelengths, opening a whole wide world of unknowns that the next 10 years are going to bring us with this facility.
Yeah, that was one of some of the questions that were asked in the press conference afterward. One of them was like, what kind of things do you think will surprise you? And it's like, we don't know. we have no idea what's going to surprise us. That's why there's surprises. We don't know what we don't know yet. So, I mean, that in itself is kind of an exciting prospect, that this ability to just keep looking at the sky all the time is going to allow us to see things that we may never have seen before.
Yeah.
So what is the cadence on this? How often does it move? What's the actual technology behind it?
Yeah, so this telescope works very differently than other optical telescopes that folks may be familiar with and used to. So we sort of have in our mind, there's an astronomer's team. They make a request. Well, I want to point the telescope here and get these data for this project. This survey way of implementing the Rubin Observatory and the Simone Survey Telescope is going to be implemented in an automated way by algorithm, so that the way the sky is observed, the cadence with which it is observed, stores all 4 of these science cases. So the high-level summary is that every 3 nights, the whole southern sky, so half of the sky, will be observed every 3 nights repeatedly for 10 years. So over the course of the 10 years, you will have 1,000 images of each part of the sky that will be split between 6 different broadband optical filters. And one of the unique things, one of the really special things about Rubin, and this is reflected in that cadence in how the sky is observed, is the community-driven design. It's not just that the project staff, the leadership get to decide this is how to best run it. Hundreds of community members from around the globe were engaged for years to do detailed analyses which tested how different science would be affected by different algorithms for how the survey would be run. And so it's really a community influence survey. So the devil's in the details. Yes, every 3 nights on average, but the details of what part of the sky is seen when, under what conditions, is community informed.
I want to talk more about the community, and to that point, let me welcome in people who are watching. We have people watching from Texas, Sweden, a couple of people from California, Georgia, Pennsylvania, and Germany, and the UK. So welcome in. Thank you for joining us today. Please continue to let us know where you're watching from. I'm talking with Beth Willman, the CEO of the LSST Discovery Alliance, about this amazing first look that Rubin Observatory presented us with last week. And if you have questions for the other Beth, please put them in our comments, and we will continue to look for some of those. So, all right, okay. There is a lot of data, and then we're talking about community. So let's kind of talk about the community aspects of this. How do you see the global research community interacting with this data? Let's start with researchers and astronomers, and we'll move into citizen science after that.
So this is one of my favorite things to think about, because in part it's what the Discovery Alliance thinks about and does a lot for. So I'll start with another one of the very special things about the Rubin Observatory's LSST project, to the point of the community-centered design, is that, right, these enormous images are coming in. For anyone that saw the first look press conference, you can't even see one single image on your computer. It takes 4,000 HD TV screens to see one of these images, and you're getting a new one every 40 seconds for every night for 10 years. So it's a huge volume of data. So the project knew this. They invested a lot in turning the images into science-ready data products to serve to the community through a science platform. And so anybody around the globe with data rights can log in to this science platform that the project has provided. And guess what? 1 week after first look, the very first preview data products became available through the science platform. And so that was just yesterday. So the community is now able to already get their hands on some data from the commissioning camera. So it's a smaller version of these very large images, but science quality, same format. So the community can really prepare and do some preliminary discovery on these early data. So a lot of science will happen through that science platform. However, this is a whole new way of doing science. The answer is not just, going to be the science platform. It certainly isn't bring the data to your computer, because you literally can't do that, even at the catalog level. Mm-hmm. So the standards and the culture around the cutting edge software and data knowledge and infrastructure that the science community needs to really fully explore all the great questions and ideas there are for these data, as well as the global collaborative networks that have developed over the last 15 years to prepare for these data, is going to be a really different mode of culturally interacting with the data. So you're going to bring your software to where the data lives, in the cloud likely, could be on-prem at large data compute centers, at some independent data access centers, and what Discovery Alliance is adding to really create the conditions for incredible ideas for LSST to thrive, so the community can harness the transformative power, is to bring in these additional, cutting edge knowledge, infrastructure, and collaborative networks.
So really quickly, before we get into sort of the Sky Viewer and some of the citizen science opportunities here, tell us what the LSST Discovery Alliance is and what its mission is, what its goals are.
Great. And so we're part of the sort of three-pillared ecosystem. We have the federally funded NSF and DOE project that built and will run the survey. Then there's the science collaborations, thousands of scientists self-organized around the world, and then the Discovery Alliance. So our role today is to make sure a diverse global community has access to the resources needed to answer their questions about Rubin's LSST, to really create the conditions for them to thrive in this unique, completely new era for science. And, we were incorporated 22 years ago to begin the LSST project, to design and develop it, and incorporated in the state of Arizona. Research Corporation, the National Optical Astronomy Laboratory at the time, University of Arizona, University of Washington were the founding organizations. And then once it became, a $1 billion scale construction project, a consortium of research institutes around the world isn't the best place to deploy a $1 billion taxpayer funded project. And so a professional managing organization then stepped into that role, and we get to focus on the science. So I've been, for the last 18 years, through all these different pillars in the ecosystem, from my earlier days when I focused on research.
So this is just there's so many moving pieces to this, not just for the telescope, but also just managing all of the data. And this is a massive project, and one we've been looking forward to for a very long time, obviously. Okay, so let's talk about the Sky Viewer. So that was also introduced at the press conference. I haven't had a chance to play with it because I'm afraid that I am going to suddenly, find myself 3 hours down the road going, what did I just do?
Yes.
But tell us about Sky Viewer. How can people already use that to explore the images, and what's coming next for it?
Okay. Yes. I did play with the Sky Viewer. So especially for the I told you that my first love from first look was the asteroids. The cosmic treasure trove image, that 15 square degrees around the Virgo cluster, is extraordinary in the Sky Viewer. Because, you might have been watching the press conference on some screen, and it looks good, but you can't really get into it. So the Sky Viewer is amazing. It's available. And one of the points made in the press conference panel that stuck with me is somebody said, well, can we make discoveries in the Sky Viewer? What does that look like? And Claire Higgs, who works for the project and their education and public outreach team, said, explore around, and at the very least, the galaxy you care most about, the thing that you zoom into to admire, you might literally be the first human to ever spend time appreciating and taking a look at that specific astronomical object, which I feel for me really places us in perspective in the universe and our place in it. I thought that was a really cool comment.
I do remember that comment and thinking that is really a good way of putting it. It's not necessarily that these things are unknown. It's that no one has taken the time to really look at them.
Yes.
It's like, oh yeah, we know there's all these stars, but no one is focused in on that star or that galaxy or whatever. So that's amazing.
Yeah. And so then in terms of what's next from the public's perspective, I just saw, it was either today or yesterday, the very first citizen science investigation has been released. So have you ever heard of Zooniverse?
Of course.
Which is for a lot of, so if you go to Zooniverse, even right now, after this conversation, and you go to the list of projects, there's a comet catcher. And that's using the data shown in the first look, is to help the project find comets in that early data set.
Okay. So that's kind of one of those solar system pillar objects that people can now go hunt for. So there you go. If you want to participate, there's one option for you.
Yeah.
How do public engagement tools like these, how does this help democratize astronomy? It's a very important thing for a lot of us in the astronomy community now to make this more accessible, to make this more open and more easy for people to participate in without 7 years of a PhD. Yeah. So how does Sky Viewer add to that?
Yeah, so for me, Rubin democratizes astronomy in two ways. One, are tools like the Sky Viewer, the citizen science investigations, which, we're barely scratching the surface. It's going to be, probably a year or two before they really start coming out in full force when more data have been accumulated. I think there's going to be very rich opportunities for anyone to engage in research. I hope to see these sort of not data influenced, data-based inquiry being in classrooms from, high school to college. And really a way to have students from any background in any sort of academic setting to feel the power of discovery. And even if they're not going to be astronomers, I don't even mind that so much when thinking about, secondary and post-secondary education, but to understand that the natural world is knowable and that there's ways that we can learn about it, and then to feel personally empowered to be curious and ask questions about it. So these tools are really going to open that for the public.
That kind of answers my next question, which was, what's your vision for educational outreach with all of these ginormous data sets? Like, you kind of have said it now, like you want high school students, elementary school, you want anybody to be able to just sort of like get in there and look at it. So that is fantastic, especially with the amount of data. And I cannot stress how much data this is going to collect.
Absolutely. And I'll tell you a little known thing about me. I was a professor at a liberal arts college for 7 years before taking my managerial role on at the project, which was 10 or so years ago. And, my science is going to be revolutionized by this. That's sort of what got me into it. But one of the things that really grabbed me coming from, teaching undergraduates at the liberal arts college was the potential this has to revolutionize undergraduate education in the country, and not just at privileged institutions, at community college and otherwise. So then I started to get even more interested in the impact on the people, in addition to the revolutionary science impact it will have.
I did some master's work on scientific education, and I have to say that I really loved learning new ways to teach and new ways to share information so that more people could access it, could understand it, it was one of the things that I really focused on I was teaching geology. So I really wanted people to have hands-on experiences with the work we were doing and not just a worksheet. So I really love all of these ways that it has opened up for students to participate. And we have several programs at SETI that do that as well, a community college program, internships, all of these things. It's fantastic. But I also like being able to kind of take that out of a science student setting and just play with it, see what happens, learn, explore. So I want to take a few audience questions. We're kind of getting to the end of the time here. So this one, I honestly wanted to ask you this anyway, so I'm gonna ask it. Zapfan is asking, any bets on how long until Planet 9 is found? And I know that is one of the things that a lot of the Planet 9 researchers are hoping for, is that Rubin Observatory is going to have all of the answers.
Yes, and I think this is one that was thrown to Joko as well during the press conference panel, if I recall correctly. So if there's a Planet 9, Rubin is going to find it. How long it will take, it would be within the first couple of years, is my understanding.
So 10-year survey, first couple of years. You heard it here. That's what we're going.
I mean, within year one, more optical observations of the universe will have been made than all optical and infrared telescopes from Galileo until now. So there is going to be a rapid increase in especially solar system science and understanding.
I feel like this is going to be this is exponential growth we're looking at. Yes. So I'm really excited about that. Okay, I've answered where the Sky Viewer is. I have put that link in in our response to the comments. And if you're not seeing it, it's really easy. It's skyviewer.app. Yeah. So
and there's a tutorial there as well. I highly recommend the tutorial. I mean, I'm an expert and I took it and I really enjoyed the tutorial walk through the sky before.
I had to stop myself when I was getting the link, because I'm like, no, don't play with it right now. Play with it later. Thomas Hill is asking, and also Astro Frank kind of asked a similar question. Is there a viewable site with specifications for VR or imagery for Rubin? And also, if there are any technical details about the telescope that you could share.
So there's an excellent website with all the technical details of the telescope and the camera and the survey, and that is rubinobservatory.org. I highly recommend that you go there and you play around. There's all sorts of information going far beyond first light. And I'm not sure if there are VR specifications available. If there are, they'll be on that website. And if they're not, there'll be a contact email for you to ask the question.
Fantastic. So other things to look forward to there. All right. We've kind of come to the end of this. Thank you for joining us today, but I do have one final question for you. Mm-hmm. What are you most looking forward to as LSST ramps up and we really get into this survey?
Great. So I'll be brief, but I do need to give you three.
Okay.
And so the first one is in my own research field of near-field cosmology and ultra-faint dwarf galaxies. So back in the day, I used sort of a precursor survey. We found the first ultra-faint dwarf galaxy, fewer stars in the whole galaxy than light coming out of a lot of the stars we see in the sky. It would take weeks of time and months of computer analysis to get the data on the stars to study these objects. And it's just going to come out in these catalogs. So the lowering the barrier of entry to cutting edge science for people at any kind of institute and revolutionizing cosmology. So exciting. Number 2, the unknown unknowns. The fact that ultra-faint dwarfs are the most numerous type of galaxy in the universe and the best tracer of dark matter, that was unknown for a precursor survey. What's the next big unknown? I don't know. And then finally, because science got me in and the people had me stay in Rubin Observatory LSST work, I'm so excited to continue to learn from this incredible emerging cadre of early career scientific leaders around the globe, seeing how they take advantage of new technologies in AI and in software engineering and pave a new way of what science looks like. I'm excited to learn from that.
I am excited right there with you about all of these things. And as a planetary scientist, I'm still going to be jaw-dropping over the asteroids and wow, the fact that so many were discovered in such a short amount of time. I cannot wait to see what our asteroid catalog looks like in 10 years. It's going to be unreal, and that will be just absolutely amazing. So I'm very excited about that. Beth, thank you again for joining us today. We are, like I said, incredibly excited about the future of the Rubin Observatory, the LSST, and all of these amazing future scientific discoveries, some of which we can predict and some of which we cannot. So thank you again for joining us. This has been so much fun. I'm glad we made it work out, and I'm really looking forward to what else your group manages to share with all of us.
Thank you for having me. It's been a lot of fun, Beth. Thanks everyone for joining.
So to our viewers, if you'd like to see all these images and their videos, the full press release is in our show notes, linked on YouTube. So if you want to take a look, you can go through all these videos yourself. If you didn't get to see them during the press conference last week. If you enjoyed the conversation, please like it, share it with your fellow space nerds, subscribe for more space science interviews like this one. Next week, we are, well, actually, no, later this week, right? We're doing a special one today. So later this week, Bettina Forget will be here with our SETI Air artist, Jennifer Willett, who did the amazing artwork for the Drake Awards this year about the origin of life. It's called Dreams of Biogenesis, and she's going to talk about her process. And there's even a video, so you can, there's a video component to this piece of art. It was amazing. I can't wait to share it with you all. That will be this Thursday, so join in there. If you want to support the SETI Institute, we are a 501c3 nonprofit. Your bits, your subs, your super chats, your stars, all of these things help us keep this program going. Thank you so much for all of your contributions and for watching. Please, if you have the ability and the desire, go to SETI.org.give now or donate and help us out. And also click that newsletter subscription. You get stuff straight into your email box. You don't have to wait and hunt it down. We will share it directly with you. Until next time, everybody, keep looking up, stay curious.